we're now going to apply our knowledge of, in particular, second order differential equations to model the spring mass system. And of course, this is a linear model, right? The differential equation is linear. So we'll start with some preliminaries on the spring mass system. More generally, many dynamical systems, physical systems that depend on T, may be modeled by the differential equation that you see here, where A is a constant, B is a constant, C is a constant, and you have a non-homogeneous term, where you also have initial conditions of this IVP. At T equals 0, you have initial y is equal to y naught, and y prime is equal to this y1. So many dynamical systems have this form. So our extensive look into second order differential equations in particular, and those with constant coefficients, is useful. Now the function g of t is called the driving function, forcing function, or input of the system. And the solution of the differential equation that satisfies these initial conditions is called the response or output of the system. That's just some terminology that one will hear, in particular in an engineering context. So let's look at the basics of the spring mass system, and we'll start with Hooke's law. Hooke's law tells us that the force that a spring applies, or that you would apply to keep it in equilibrium, is proportional to the spring displacement from equilibrium. Okay, here this minus sign means that this is the force that the spring applies. Okay, and what that's telling you here is that this minus sign is restorative. Okay, so if a spring has a natural length of lowercase l, so if we just put the mass right there, okay, at its natural at the natural length of the spring, you won't get any force, and the system will just stay there. If you compress, and that's where we call x equals 0. Okay, that's important. So basically, when the distance from this wall to the mass is L, that's what we call x equal to 0. So x is extension or compression, elongation or compression from the equilibrium position of the spring. And so if x is negative, if we compress the spring, okay, so x is negative, then this force will be positive. It'll point to the right. On the other hand, if x is positive, such as what we have here in the diagram, then the force will point to the left. Okay, it would be negative. And so this is a restorative force. The force of a spring is a restorative force. The spring always applies a force to get back to the equilibrium position. Okay, it could be to the right, it could be to the left, depending on whether we're dealing with elongation or compression. K, this constant of proportionality between the force and the extension from equilibrium, is called the spring constant or stiffness. Okay, it has units of force per length. One may choose, okay, so this is kind of just as an aside, something to know, okay. One may choose an aging spring and use, for the spring constant, a non-constant, okay, so you could take the spring constant to be non-constant and set it equal to k times this exponential negative alpha t, okay? So as time goes on, this spring, the stiffness goes down exponentially. Okay, it's just a model. We could have also chosen other ways to reduce the spring constant, okay, and have a variable stiffness. But this is just one, okay? And another one is like if there's a rapid decrease in temperature, the stiffness actually goes up. And you could model the spring constant as increasing linearly with time. Okay, so here you would have some temperature decreasing in time, and you get a corresponding increase in time with the of the spring constant. Also, springs in parallel come up. So if you have two springs, such as you see here, okay, and they're connected to this, connector between them, and that's connected to a mass. Okay, you could just you could consider these springs massless, okay, as an approximation. So the mass that we're dealing with is much heavier than the mass of the springs. So if they're connected in parallel, which is exactly as you see here, okay, and you have two different springs, and in general they could have two different spring constants, the displacement will be the same in both of those springs, but the force could be different, right? In general, it'll be different if K1 does not equal K2. Well, we want some way to simplify our discussion, okay? And so we're going to talk about this effective spring constant. So if we put a black box around this and pretend as if it was only one spring, and we just look at the force applied from this black box of a spring, okay, it's going to follow this form. That's how we define the effective spring constant for this system in parallel. But if we open up that black box, we'll see that there are actually two springs, okay, K1 and K2, and the forces sum from those two springs. Now x1 is equal to x2 is equal to x. Let's just call that x. And so you could factor that out, and you get this expression here. And setting this left-hand side equal to the right-hand side, getting rid of the x and the minus sign, you get that the effective spring constant is K1 plus K2. What does that mean? That means if you have a system of springs in parallel, all you have to do is sum the spring constants and just pretend there's one spring there. Okay, just treat it as if there's just one spring with the effective spring constant being the sum. What about springs in series? Okay, here we have a spring K1 and a spring K2. They're connected to each other, and a mass is connected to K2. Now, if you extend this system and you just kind of hold it there, okay, the system's in equilibrium. K2 is not accelerating, the first spring's not accelerating, the mass is not accelerating. So actually all the forces, the force that K1, the first spring, applies on K2, and likewise that K2 applies on K1, okay? And the force between K2 and the mass, okay, all of those forces will be equal, okay, by Newton's third law. So you have them in equilibrium, and you'll have these forces being equal to each other because nothing's accelerating. So here the forces are equal, but the displacements, so K2 could stretch a little bit more than K1, or vice versa. So the displacements are different, but we do have about the displacements that the total displacement x, okay, so the total, if we have natural, if we have a natural length, right, and we for both of these springs together, and we extend away from the natural length of both of those springs together, so that natural length of both springs will be the sum of the natural lengths of each spring. So if this x is the total extension, okay, of both springs, it's going to be equal to the sum of each spring's extension, x1 plus x2. Okay, so this is what we have there, all right, that relation. Now we're going to define the effective spring constant as we did previously, in the sense that we're going to put a black box and just pretend like it's one spring. So here you apply a force, or the spring is applying a force, and if you divide by the effective K, you get X by, and here we're just looking at magnitudes, but by Hooke's law, you would get X. Now you know that total extension of this black box spring is, you take off the black box and you see that it's a sum of two extensions, and each one of these by Hooke's law. So this first one's equal to F over K1. Now it's actually equal to F1 over K1, and X2 is F2 over K2, but they're all equal. So you get this same numerator there, and you could divide it out, and you end up with this relation. So they reciprocally add. And this relation, you could take the reciprocal, and you get a common denominator, and you get that. Okay. So what is this telling us? If you have two springs connected in series, as you see here, you could really treat them as just one spring with the effective spring constant of that. Okay, that's what that's telling you. Now, a quick word about phasors. Okay, now phasors are a way to kind of represent cosines and sines as vectors in a sense. Okay, vector where? In the complex plane. Okay. So we have from Euler's formula here that e to the I theta, which is the phasor there. Like if you multiply this by some constant, you could change the length, is equal to cosine theta plus I sine theta. Okay. You could kind of think about this as like the x component and the y component of a vector. Okay. Because this is the real and this is the imaginary part. So combining sines and cosines can get tricky. So one trick is to represent these sine and cosine terms in the phasor space and add and subtract, or vectors or phasors in this phasor space. So you treat it exactly like vector addition and subtraction. And from there, you could look at a projection from the imaginary or real axis of whatever you add and subtract, and you could then get the sum. Okay, well, let's look at concretely something. Okay, say you have this term right here. Okay, and you don't want to just have these two terms like that. You want to add them to get, say, a term that looks like this, just a cosine with a phase angle and a constant in front. How do you do that? Well, it's kind of tricky again to add cosines and sines, but what you could do is represent this cosine here as this phasor. Okay, and why could you do that? Because the real axis, if you look at the real axis here of, so this e to the I theta is this phasor or vector, if you will, in the complex plane. So cosine is just the real part of that. Okay, that's the real part of that vector, and so that's what you're seeing there. Now, we want to relate everything relative to this cosine, so sine of theta is cosine theta plus pi over 2, and there you see a 90-degree angle, so that's how we represent the sine. So this phasor or vector in the complex plane represents sine omega t. And in dynamical systems where t is time and omega is this angular frequency, as we'll see, you could view this system as rotating. But anyway, if we want to add these two terms, what we could do is just add them as vectors, okay, and that'll give us the projection of, and then once we add these as vectors in this vector space or the phasor space, we then look at the projection on the real axis to get the cosine. Okay, so it's just a way of adding trigonometric functions, honestly. So if we do that, then we're going to have that the length of this vector, well, here's the x component of that vector, and here's the y component, because we're adding vectors. And so the length of this vector is going to be by the Pythagorean theorem there, the hypotenuse of triangle that you would get from combining these two phasors. Okay, and so that's where you're getting this C1 squared plus C2, because each of these has a length of C1 and C2. Okay, this sine omega t is what you would get from projecting onto the real axis. Okay, so that's how we'll get the A. And what if we want this angle? Well, here you're going to use opposite, which is C2, and adjacent C1, and use the relation tan phi is equal to C2 over C1, and that's how you'll get phi. And so this is how you could combine these two terms into that, okay? A is called the amplitude, phi is called the phase angle. Now in engineering and in physics texts in particular, you look at projections onto the real axis and you're dealing with cosine. You'll also find texts that don't want to combine these two terms into a cosine term, but rather a sine term. And if you want to do that, the amplitude is the same, but you'll have C1 over C2 instead of C2 over C1, okay? Sine here is the projection onto the imaginary, and that's why that's happening. But anyway, so just to keep that in mind, if you actually want to combine them to a sine, you would use this for tan for the phase and not this, okay?